Hi, hi, and welcome back. We're going to continue our discussion with graphing vector fields. And as we said in the last video, graphing a vector field is the same as we did last year when we talked about slope fields. There is a difference. We'll talk about those again. But an important thing to remember, the main difference between a slope field and a vector field is that a vector field, remember, has both direction and magnitude. So it's important that we get the direction of our vector fields in, and we get the length. Now the length should correspond to the magnitude. So if you have a smaller length, like a magnitude of 1, that should be smaller than if you have a magnitude of 2. So you can use length to represent magnitude, or you can represent, we talked about thickness. You can make them both the same length, but just use the thickness of your arrow in order to correspond to the magnitudes. Now, when graphing in 3D, we're going to use some technology. So I have a couple of little things here you can scan. One is using Desmos, and the other one is GeoGebra. So let's go ahead and look at what the vector field for this vector would look like. Remember, this is a vector field, and remember what a vector field does. It is going to give me direction and length of each little part. So what this is going to do, kind of like a vector field, it's going to give us an idea of what direction our particle or whatever is moving at any given time on a certain function. We'll talk a lot about that. So I'm going to go ahead and use my phone and scan this. Okay, so let me see here. I'm going to go ahead and scan this. There it is. And it takes you to the GeoGebra vector field one. And we're just going to type this in. Now, of course, this is a different function. But if you come down here, now notice, here they're saying P is my change in X's, Q is my change in Y's, and R is my change in K's. So I just have to retype these in. So for the first one, hold on. There it is. Okay? Maybe not. When technology isn't your friend. There it is. There it's working. Okay, so when I type this in, my P is going to be 2x. So I just type in 2x. Go to Q. Our Q here is negative 2y. So I just type it in negative 2y. And I type in R. Our R here is negative 2x again. So I think it should be negative 2z. So let's go make it negative 2 and we'll make it z instead. Okay, it's at negative 2x, but we're going to make it a z. Hit done. And look at it, there's our vector field. Now if you notice here, and like GeoGebra, if you can look at this, you can kind of mess around with it, move it around, and you can kind of think. Look at this right here. And let's look head on, and you can kind of see it right here. And you can get the directions of it. And if you notice, take a look here. Over here, look, they're moving away here. Here they're moving just straight up and down along the z-axis, up and down the z-axis, perpendicular to the x-axis, it looks like. And you got these little arrows up here. These little arrows here that represent. So what do you think these little arrows represent here? Yeah, they have different lengths. So notice these up here, they're going way forever. So they have a much longer length for us. So the length of each one of these little lines represents a different magnitude. So play around with this. Change these numbers around if you want to. Just kind of see what would happen to the graphs and what would happen to them. All right. Anyway, so that's GeoGebra right there. So yeah, definitely go ahead and play around with that. It's kind of fun. You can also use Desmos. Desmos has a really good two-dimensional one. All right. So let's kind of continue on what's going on here now. So let's remember what we talked about earlier this year. We learned about gradients. And you might remember that the gradient is a vector formed by the set of partial derivatives. So, in other words, what do gradients do? We talked about this. They give us direction. Now, they give us a very special direction, which we'll review that later on. So remember that a gradient gives us direction. And this is similar to finding the slope from calculus last year. We learned how to find the gradient, and remember we had a very special symbol for it. So we want to find the gradient of this function right here. We call it del f of x, y. And if we find the derivative, the partial, with respect to x, we just get 6x y minus, this just becomes y squared, comma, find the partial with respect to y, 3x squared minus 2xy. Remember, we're going to be looking at the partial with respect to x and the partial with respect to y. So that's what the gradient finds for us. Now you might be asking yourself, why are we going back to the gradient? Well, remember, let's look at the vector field. Well, what is the vector field again? It gives us also direction. It gives us slope. So what do you think makes up the part of the vector field? It's our part of our gradient. That's right. So this would be like my change in x. That's my fx. This is my change in y. That's my fy. So a vector field, in some ways, could be considered is also the gradient. And we're going to talk about if they are the same in just a few moments. What happens if they are the same? So we can easily find the gradient right here. So let's see here. Given a function, we can find a gradient vector field. So let's remember this, right, of gradient right here. Remember, a very important aspect of the gradient is that this gives us, and you might remember this, the steepest, the direction of steepest ascent. Now remember what that meant. In a three-dimensional space, like if I'm on a flat plane, what's the direction of steepest ascent? If I want to get this off the fastest, we would go perpendicular. So that's what the gradient gives us right here. So the gradient gives us the direction of steepest ascent. So we want to find a gradient vector field. So they want us to find the direction of steepest ascent and the vector field attached to that. And it's super easy. In this case right here, the gradient vector field is just the vector field that gives us the direction of steepest ascent. So it's not too hard to do. So in other words, we're saying that the gradient will equal our vector field. And that's what this means right here. That the gradient vector field, we're saying that the gradient is the same as our vector field itself. So let's go ahead and find the gradient fields for the following, so it's not too hard to do. So my del f is the same as my gradient. That's what this is saying. And this is going to equal, well, the derivative with respect to x only, 2x sine 5y. And then we want the derivative with respect to y, which is just going to become 5x squared cosine 5y. And we can do it in any dimension. Let's try it with 3 dimension. Ready? We're saying that the gradient has to equal our vector field. Ready? The derivative with respect to x alone. Be careful here. That's a negative x. So we're going to get negative y times z e to the negative xy. The derivative with respect to y, negative x z e to the negative xy. And the derivative with respect to z, well, everything else just, this is like a constant then, we just get e to the negative xy. Very easy to do these. So remember, this is my partial with respect to x, there's my partial with respect to y, and there's our partial with respect to z. So a gradient vector field is just our gradient in the same direction. So basically these are going in the same direction. And we're going to talk about that in another video here, okay, later on. So how to sketch a vector field? Well, we want to sketch the vector field as well as several contours. So let's go ahead and just get what the vector field is going to be. So to sketch the vector field, again, we can kind of think of this as the slope. So I'm going to say that my gradient is the same as my vector field. And that's going to give us 2x, 2y. And ready? Let's take a look here. Let me go ahead and graph this. Let's go ahead and graph some contours here. Remember what a contour is. We'll let f of xy equal 0. So we would just get x squared plus y squared equals 0. So there's just the point as a circle at the origin, just one point. If we let f of x y equal 1, we would get x squared plus y squared equals 1. So we have a circle, 1, 1, 1, 1, like so. 1. And let's do one more, f of x y equals 4, mainly so I can make it a nice circle here. And that's going to be 2. There we go. So we got a little contours. And now let's go ahead and graph our vector field for this problem right here. And let's see here. We're going to do the first one at 1, 0, and that's going to give us 2, 0 with a magnitude of 2. Now don't forget, at 1, 0, we're just going straight out. So at 1, 0, we are going out in this direction. Now it's going to be 2, so I'll make that a little bit thicker, right there. F of 1, 1. If I do f of 1, 1, that's going to give me 2, 2. Remember, this has a magnitude of square root of 8, which is almost 3. So over here at 1, 1, or at 1, 1, sorry about that, 1, 1, it's going to be a little bit thicker, so I'll make it a little bit wider. Oops, sorry, try to make it the same length. There we go. And we'll have an arrow. There we go. I think next time I should just do length. Okay? Alright, and of course if we go around here, this is going to be a magnitude of 2. And if not perfect, it's not perfect. Here we'll have a magnitude of 2. 1 over here. It's going to be the same direction, so you can kind of verify these. Be a thick over here. Whoops. And again, if you're not perfect, it's not perfect. That's okay. Just kind of get the idea. Negative 1, 1. Going here. Look at those arrows. Over here. Going straight down. And over here. There we go. Alright. Now again, if you notice, one thing you might notice here is that of course there are all supposed to be different thicknesses here, or different lengths. I think lengths might have been slightly easier and better to use in this case. But notice again, they're not all on the same circle right there, because remember, there's multiple circles that go around here. We only found the contours for nice ones. What if we did the square root of 2? Well, then we would, of course, cross right here. So we kind of see how the magnitude and the contours work kind of together. Now, other thing I want you to notice is what direction are we heading? Notice we're heading away from the circle. So this is truly the gradient. So we are moving away from the circle itself. Remember, the gradient is going to give us the direction of quickest ascent. In other words, if you're on a circle, it's going to be perpendicular to that circle. So we can catch that gradient right there. Alright, if you go to video number 3, we're going to talk about an important thing about the gradient and the vector field and their relationship with each other. I'll see you then.